right. And so students actually take over this class for the last third, the last 5 or 6 weeks, which is more than a third, where you do your presentations. So this is an unusual lab class in that we're not in a lab. We're doing this remote and virtually. So when I was first challenged with coming up, how do you do Environmental Science 22 as a remote class? Do I put on a lab coat and play with my microscopes? um, no. So I thought, let's look at the SLO. What is the purpose of this section of this class, which is a 2-unit CSU UC transfer credits as part of environmental science. So this is the lab class that accompanies Environmental Science 1. Environmental Science 1 is a lecture class, and you can either take it previous to this one or at the same time. But it's a very bad idea to do it in the wrong order, to take the lab class first and then take the lecture. In fact, the system might not even let you do that because it's a prereq. ES1 is a prerequisite for ES22 or concurrent. You're doing them both at the same time. And I think there is a section of Environmental Science 1, not taught by me, but by either the latter faculty or another adjunct for this semester. So yes, you can take them concurrently. So then the question is, what do we do in an environmental science lab if we're all looking at little Zoom rectangles? So I thought, let's look at the SLO. The SLO says the students should really, in this class, understand and be able to take apart the scientific method as it's applied to an environmental problem. And it should have all of the requisites of what you would do in a laboratory. So we know that in laboratories, people conduct experiments. We also know that experiments are part of the scientific method. They fit in there somewhere. And what experiments are is a way of testing a hypothesis or maybe imitating someone else's publication. And then they have a methodology and an experiments that they conducted. So in the peer review process, which should happen sometimes, is that then your peers will try to reproduce your results. And that's what makes the scientific method quite unique. Now, we've typically seen the scientific method applied to science, all of the so-called lab coat sciences, right? But the truth is, scientific method in terms of how you publish research and what are the standards for a scientific paper are not confined to the big sciences, to chemistry, biology, ecology, physics, astrophysics. That is where the scientific method rules supreme. But when you get into the social sciences, a lot of publications also follow the scientific method. So today we're going to outline what that is. But here was the challenge. When I first came up with this class, I thought, well, what we'll do is instead of conducting experiments in a laboratory, which we can't do, let's have every student in the class adopt a science paper, a published science paper, ideally recently published, that addresses some aspect of an environmental problem. Now, actually, that's a pretty broad category. It might sound narrow, but it's not, because what you'll see today is that a lot of publications, including social science ones, address environmental problems. So what that means is that, let me open the door at the gate here. So many bells and whistles. And let's see, the waiting room is now open, and I'm going to say, please, no more campanitas here. And so you'll find that when you look at publications that address environmental problems, sometimes you'll have an aspect of, say, public policy or economics or urban planning, which addresses an environmental problem. And if the environmental problem has a scientific basis, for example, in Los Angeles, we have in many neighborhoods a lot of uncapped or barely capped, abandoned oil and gas wells. And these are all over LA because one of the first economic booms for Los Angeles was, in fact, oil and gas drilling. I mean, we all know that because we live in LA. So if you've been down to, Signal Hill, Long Beach, Wilmington, lots of places in LA have either, when you take the, that option to the airport, instead of taking the 405, you go, Fairfax, and that way you go by the oil fields, and you can see all the little oil derricks there are pumping oil. So when the fields are empty, when the gas is used up or extracted, and when the oil is extracted, they just cap them and walk away. So some of these oil wells are really old. They've been around since the 1920s, 1930s. And now those neighborhoods are residential. There's houses and schools, and people that live there don't necessarily know that that little stump in the empty lot next door is a barely capped oil well. So what that means is that a lot of the fumes and the toxins and all that you can expect from abandoned fossil fuels actually affects the neighborhood. It affects people's health. So you might actually have a paper that's about public health policy involving oil wells that has to have in it the science of why are these dangerous. And so you'll see in the literature review, in the abstract, in the first part of the paper, these are dangerous because, and then they'll cite, research and say, Dr. Smith at USC found a direct correlation between fumes from abandoned gas wells and incidences of child asthma or something like that. So what I'm saying is do not see science or the scientific method or scientific publications as narrowly fit into lab coat science, test tubes and chemistry and experiments that you conduct on a tabletop and with Bunsen burners. And that's definitely a very important part of the scientific method. And it's what we do at Valley. We have a whole building, Allied Health and Science is full of laboratories. There's chemistry and physics and biology and the rest of it. But for our purposes, because we're doing environment, we're going to look at a lot more than that. And depending on your own interests, what I mean by that is you might already have an idea of what you want to do with a 2-year or 2+ year studies in a community college that then work as transfer credits when you go to a 4-year institution, say a Cal State or a UC or another institution. So you might already be planning, okay, when I go to CSUN, I want to major in physical geography. Say they have a very good geography department at CSUN. So let's say you want to be a geographer, or you want to do geographic information systems. So then you're taking courses at Valley that give you those Cal State credits that build toward that satisfy the requirements of that major. So for example, it might be that major says, well, you should have a course in environmental science, a course or two. How you include this class in your plans for a 4-year degree or in completing a 2-year degree, which would be environmental science at Valley, is where I think that this class will be very useful, because we're not going to restrict you to things you might not be interested in, frankly, or they're not conducive to what you want to do after your career at Valley. So that is all by way of saying, when I say something of your interest, I mean it seriously, because we all live in this world in Southern California, and a lot of things spark our interest. Just life's experience will tell you, that, well, for example, we've just experienced an incredible number of urban fires that were unprecedented and incredibly damaging in every respect, not just to people's lives and homes and their possessions and everything, but it also, because it's an urban fire, it burned structures and it burned everything in them. So that's not like a wildlife fire, a wilderness fire, a chaparral fire. What's burning is the vegetation. So that firefighters going into a wilderness area to fight a fire have to deal with incredible heat and wind and smoke and smoke inhalation, and not to mention the changes in the wind and the danger. Fighting a wildfire is very, very dangerous, and we know that from when you look at the death toll of firefighters. It's almost always in a wilderness fire. But the urban fires are completely different beasts, because we make so much stuff out of plastic and sheetrock, and there's so many chemicals and metals. And consider that every house has acetone and bleach and God knows what's in the garage, fuel for the lawnmower. All that stuff is in the house. And then the next house has the same stuff. And the next house has the same stuff. And here comes the fire in Palisades, wipes through the whole thing. Question was, is it worse for an older house? Good question. The interesting thing is that older houses don't have as many as much of this modern materials as houses do now routinely. So I would venture to say that a new house that a bit more recently probably has a wider range of materials that went into building it than an old house. For example, a typical Spanish style California 1930s bungalow is going to be wood and stucco and red tile roof and maybe tile floors and wooden floors. But a modern apartment building has a lot more than that. So the issue then comes, well, what sparked me was we want to do, my other hat is that I'm a co-coordinator for the Sustainable Environment Institute, which you'll hear more about when I show you some websites. But we sponsor during the school year a series of seminars every month. And the first one we're going to do is about fire. Now, the one we're sponsoring in February is going to be about wildlands fires and fire control, so that there are methods that people have used, particularly the indigenous people in California have used, to limit how damaging a fire can be. It's what in the firefighting world they call a controlled burn. And indigenous people in a lot of Western states were practicing controlled burns way before it became an acceptable idea in the world of firefighting, because it used to not be acceptable. The whole idea was we put out a fire as soon as it starts. But what that does is it builds up what firefighters call the fuel load, which is how much vegetation hasn't burned. And in some cases, that fuel load is 25 years old. So it's ripe for a major fire. And that's why controlled burns minimize the spread and intensity of seasonal. We used to call them seasonal fires, fire season. And all by way of saying that there is an interest, I have an interest in what happens in an urban setting when you have the materials that are left behind after the fire are so toxic that you need hazmat teams to remove the rubble. And that's what we're seeing right now for Palisades and Altadena. There is, in fact, it's like a large-scale military operation. I think there's a military person in charge of, first, how are you going to remove it and where are you going to put it? And this stuff has heavy metals. It has, forever chemicals. It has forever plastics. It's pretty toxic stuff. So handling it in and of itself is a hazard. And then where are you going to put it? So the first places they were even suggesting landfills, and there was some community pushback of like, don't bring that stuff here. So now they're dedicating an area that has never been used for dumping before as the place where they want to dump a lot of the stuff from Altadena. I don't know where they want to put the Palisade stuff, but so far they're taking it down to PCH and stacking it, I guess, along the beach. I don't know where they want to put it so that it can be hauled off. All by way of saying, as somebody who studied urban geography and economic geography, the spatial distribution of problems has always interested me. So I'm really curious as to how we're going to deal with this question of fire in Los Angeles. And there's a lot of science behind it. Whew, what a preamble. So let's now, I want to do several things today in our first meeting. One is, and let's see if look at that. This is a very good turnout. Excellent. We have 20 people. That is very good. Let me do the way I do this is I do screenshots of the participant list, which means then I don't have to, ask people to say that they're here, and that does it, because all of you have fortunately put your names in there. I'm checking, make sure there's no Zoom user or owner. There's Walter, but I guess it's probably only one Walter. Let's see, Walter. Yeah, Walter Rojas. Okay, computer science major. Oh, you're gonna love this class. Because it leads me to, okay, so that was the idea of this class before this year, where we'd adopt a science paper, we would learn how to read a science paper, we'd learn how you mark up a science paper, and then we learn how do you summarize what somebody else wrote, and then present it to a lay audience as if you wrote it yourself. So the presentations are the money shot for this class, and that comes at the end, where I turn the class over to students and we meet. At each of our meetings, we might have, depending, this class is somewhat large with 20, we might have as many as 4 presentations. Each one is 20 minutes, ideally. So we're gonna do a lot of prepping before we do these. And you'll use either PowerPoint or Apple's Keynote or Google Slides. Any of those are good. And they're all really similar. They do the same things. And hopefully along the way, we'll learn also a lot about how to use computers, how to use software to do everything from marking up a PDF file to choosing material that you want to that you select from the paper. It'll be quotes. Ideally, you'll choose a paper that has really good graphics. So you'll crib all the graphics from the paper, put that in your slides, and then you'll discuss. Well, when we get closer to this, I'll flesh this out, and you'll be much more comfortable with the idea. And that is, we don't have a final exam. We have a midterm, but we don't have your final exam is your presentation. So here I have to make a major request, which is, it's not a request. It's a threat. Every student in this class is going to do a presentation, and it's going to run for, say, 5 or 6 days or weeks when we meet once a week. So it's really important that even when you've done your presentation, let's say you went day 1 and you're done, which means you're actually done with the semester because there's no final, please don't not show up to class, because everyone in the class owes it to everybody else in the class to listen to their presentation. It's just a courtesy that we owe each other. So what I love about the presentations is that I often don't know anything about what the student is presenting about. So for me, it's an education. I'll give you one example of how much fun this can be. We had a student, was it last year, the year before last? No, maybe it was last year. And she chose to discuss something that is really interesting ecological research that I had run into in Environmental Science 1. That we could look at it this way: do trees talk to each other? And the science says yes, they do. And you're thinking, oh yeah, really, what? And she laid it out. She had she chose a paper on mycorrhizae, and mycorrhizae are the little funguses that grow in the roots of trees. And it's through the mycorrhizae networks in soil that trees in a forest, quote unquote, talk to each other. It's also true that disruption of mycorrhizae affects the health of a forest. And it's also true that the mother tree in a stand of trees has the most developed mycorrhizae. So we were all like, really? What? Trees talk to each other? And with a lot of detail. So there's all this experimentation she showed on how you can test that the mycorrhizae transmits information to a different tree. And in her slideshow, she even showed that mycorrhizae allow trees of different species to talk to each other, which was a real wake up, meaning there's a redwood tree, it's got mycorrhizae in its roots, but it's talking to a maple tree. So we were all flabbergasted, because even if you'd heard of that before, she gave such a good presentation that she stole the show. It was wonderful. So that's because she was really interested in it. You could tell it really caught her attention. She really liked the topic. She had great slides and photos, I guess, slides that are microscopic, because mycorrhizae are tiny. So that's what you'll be doing in the last 5 weeks. I'm estimating if we're 20, we're actually supposed to be 23, but let's say we're 20 students. It's not bad. I don't want to say, oh, let's do like 5 in one day. That's overwhelming. 3 is good. 4 is sometimes a stretch. We do have 3 hours and they're only 20-minute presentations, but I think that squeezing too many in puts pressure on people that are presenting. They're looking at their watch thinking, I'm going to run out of time. And it's too much information for all of us. It's like, how do I process hearing 5 slideshows on 5 completely different topics? So that's why I'm going to do, 4 max and spread it out over, 5 days, and with 20 minutes a piece for each one. So that is where we end up. AI. And so I took advantage of the fact that the district was offering several webinars to faculty to better understand AI in the classroom, AI in higher education. And what I had to do was learn really fast, because I knew nothing about AI other than little pieces in the newspaper, or, that DeepSeek is almost bankrupting ChatGPT. But I didn't know a large language model from a generative AI model. And so these were really, really good webinars. And the last one I took, the person who led the webinar said, look, AI is here to stay. It's not going to go away. And you can't say, well, you can't you can't use AI in this class. I mean, for starters, students are, if they know how to use it, or even if they know how to use it a little bit, they're going to use it. I mean, it's like telling somebody not to use a word processor, to write an essay. It's almost like that. I mean, the technology is there. It's not going away. It's readily available, and it helps people get a lot of, work done. That said, there's a lot of pitfalls. There's a lot to understand, and in fact, it's why it's so controversial. So I learned up as much as I could, and that's why what I'm going to share with you now is I have to say our syllabus is a work in progress because the more I learn about AI, the more I'm able to plug in articles and relevant material as we work our way through. So I'm going to do the share to our Canvas page.
So here is our syllabus, such as it is for fall 2025, for Environmental Science 22, and this is for the synchronous section on Wednesdays, 1 to 3:55 p.m. Let's make it 4. Um, so it's straightforward pretty much. There is a link to a PDF version of the syllabus so that you don't always have to be online to see what's in it. And calling your attention to the menus on the left side, you'll notice that there's no Zoom. There's no Zoom link, no Zoom tab. And that's because Zoom in Canvas does not work very well for me. Every time I create a Zoom meeting through Canvas, I can't go back and edit it because Zoom tells me I'm not authorized. I've tried to work this out for years and they'll never work it out. So we're just doing it this way where the link you've used to get to class today was actually put in the announcements. And that is the same link that we will use every week, barring any disasters, so that you can put it in your calendar and it's the same link every week from 1 to 4 p.m. on Wednesdays. We don't have any significant holidays this semester, so you'll see I've tried to fit everything into our syllabus with our existing calendar. Um, I was confused as to whether we're a 2 unit or 3 unit class. Now my announcement says that it's 2 units lecture, 1 unit lab, so that adds up. In other words, we do have 3 hours a week. And they're the prerequisites that are spelled out in the beginning part. And the only thing is, of course, to have either taken Environmental Science 1 previous to ES 22 or concurrently at the same time. So you might this fall be taking ES 1. I think there's more than one section. In addition, then you're taking ES 22. These are our SLOs, student learning outcomes. And this is what has helped me make an online version of a lab class, because obviously we're not in a lab. So the idea here is how do we meet our student learning outcome with an online class? And that is what we've achieved for the last few years through ES22 remote. And as you'll see, we've really taken the SLO quite seriously, and I'm quite confident that when you've taken this class, and it is a transfer class for Cal State, UC, and GETSI, that it satisfies what these requirements are. The main idea is students should be very familiar with the uses of the scientific method, particularly in relation to examining, analyzing, solving environmental problems. So that's the only condition in our approaches that our selection of articles and our selection of papers and so on should be addressing environmental problems. This is the current calendar for what are the deadlines for dropping and adding. That's all in the syllabus. They have added this section on disenrollment. I think this had to do with payment of fees. And this would be what would prevent the district from disenrolling you. And they have um, five conditions in which you will not be disenrolled. But otherwise, they do want this to happen earlier in the semester than we used to. So we used to wait until census week, and census week was often the third week. That said, um, I will be very careful to look at who the participants are for our first class meeting in case we have people on a waiting list. So far, from what I downloaded in the roster, there's nobody waiting to be added to the class. So as a result, I don't quite have permission numbers yet. But should that happen, and then they issue permission numbers, I would drop all the no-shows. And the definition of a no-show currently with Valley is students who didn't come to the first class. So they're very concerned about that because we've had a whole problem with bots signing up for classes and they aren't real people. And community colleges all across the country have had this problem, not just us, and they're trying to implement some kind of measures to prevent bots enrolling in our courses. It's a scam that obviously involves money. So let's get to the brass tacks, our required text. There is no required textbook for the class, meaning there's nothing in the bookstore. That said, everything will be posted online, as you see here. And what you can see is we have one, two, three, four, five papers that are addressing what are scientific papers structured like? How are they written? What do they look like? How do you know you're looking at one when you're looking at one? And that is something we will focus on in the first few weeks of class. We'll read these in small groups. They are pretty much short papers. I don't think any of them are really long. And it does show you to what extent um, uh, a, uh, a science paper has a certain rigorous structure to it. And we want to learn to do that because we're going to take them apart. The outcome, the takeaway from this class will be that you will have overcome any kind of fear you have of a science paper by seeing how they are written and being able to even take one apart without understanding what's in it. That's what is in a sense, the beauty of this method is that it has a very predictable structure. And that makes it easy to go from the title to the abstract to the introduction, which often includes a literature review, which situates the paper in a wider body of work conducted by previous publications. And then after they've situated the work, they advance a hypothesis, and then they go through all the processes of testing a hypothesis, the experimental method, etc. And then they discuss their results, and then they go to a conclusion. So that is a consistent structure. There are minor variations, and we learned, for example, Environmental Science 1, that there are 7 parts to a science paper. And you'll see today the first video that we'll see shows 5. So it depends on what gets lumped in and what gets emphasized. So some of these shorter ones, they lump together, for example, data, data analysis, and discussion are all going to be one item. We like to see them as separate ones because it helps us mark up the paper. And that is one of the things we will learn how to understand them, but also how to mark them up. There are 2 more readings, at least here, and there's more than that when I'll show you in a minute, on the writings of Thomas Kuhn, who's a we say historian of science, who's really helped people understand how science changes over time. And it's very important because Kuhn's contributions remain very important and valid to this day. How do we understand changes in science? What governs the rules? What are the guardrails of scientific discourse? Who's in, who's out? What's acceptable? What's unacceptable? And we learned that from reading Thomas Kuhn. These aren't equally long. I think the Stanford philosophy one is lengthy, but you'll see by the time we get to that you'll be able to, in a sense, I won't say skim through it, but you'll be able to jump around to see what addresses the questions we have. Now, the difference this year with ES22 previous years is that now we are, in a sense, embracing AI. Not because we love AI, but because we don't have a choice. And it's very important. It behooves us to learn a lot about artificial intelligence and what role it plays in our education, specifically what role it plays in science and even in environment. So there is a link. In fact, this header is a link, and it will take you to the backup site. It's more like a repository, a little library that is not in Canvas. It also has no login, no password, no guard. You can just go there, and you can see that it has has a very long list of articles on AI. And what I like using about this repository is that I can constantly update it without having to go into the modules in Canvas and then go back into the syllabus. And this makes it very easy to just put an announcement and say, okay, we've updated the article list. It kind of covers the map. The main one that you'll see we'll talk a lot about is the emergence of Google's Notebook LM, which is I think, a huge game changer. This is something I used in my summer class for ES1, an asynchronous ES1 class. So it is a bit tailored to that class, but it basically discusses how you use this page and how you interpret work that's done by AI, good and bad. And by the way, there's a lot of bad, meaning a lot of it is wrong. A lot of it is what they call hallucinations. AI is not intelligent, and that is something we all need to get into our brains. AI puts together things it finds from what's called a large language model. So it reads and it compiles and it puts things together, but it doesn't reason, it doesn't discern, it doesn't really have much by way of a memory, and it's not intelligent. In a way, it's a service. And because it's very, very fast, people are using it a lot, and in some cases excessively, meaning that they put too much faith in the product. They think that it's accurate, that it's correct. But I ran into, in fact, I think that's covered in this video. I ran into being gaslighted by Meta, which is the AI that Zuckerberg has created in Zuckerberg land. It's a chat. What's nice about Meta is that it's kind of chatty, but it gets things way wrong. And so I started to test it and realized, okay, it does get things wrong. So I encourage you to do the same thing. One of the things you might do with either ChatGPT or even Meta is to ask it a question that you already know the answer to, and that you know the answer in detail, and then see how close Meta or ChatGPT get to what you actually know is the right answer. And twice Meta has failed me in this regard. Um, and that is discussed a little bit in this particular short video. I asked Meta what had happened to, well, if you're all following the Epstein scandal, you know there's Virginia Giuffre, who was the victim of the Prince Andrew more than once. And her testimony is what, in a sense, sank the Randy Prince. Um, and she went on to get, harassed and threatened after she um, came forward. And um, and then from what I had read, that earlier this last spring, that she had taken her life while living in Australia. It's mysterious because her family was nearby and there was no indication that she was experiencing the kind of distress where you would worry she might be suicidal. And as a result, it came as a surprise to her family members. So I asked Meta, what happened to Virginia Giuffre? And this is in July. And Meta says, Virginia Giuffre is alive and well and living in Australia. So I went back to Meta and said, no, that's not true. She died, allegedly taking her own life in April of this same year. And then Meta answered, yes, if I knew then what I know now. Thought, well, that's an easy one. So you can't trust it. At one point, I asked Meta, name 5 contemporary African American intellectuals and scholars who write critically about society and about politics. It gave me a list, but it wasn't contemporary. It was 1960s. It was way out of date. So it doesn't know everything. It'll try, and sometimes it'll actually tell you, this is what I tried to do. Now, ChatGPT, on the other hand, will actually, if you ask it to, it will report back to you everything that it did in order to retrieve the information. And even though it is, supposed to be chatty, writing a query or a prompt, as they call it, in ChatGPT is very important for the quality of what it brings back. So one of the things you want to learn to do with ChatGPT is how do you compose the right kind of prompt that will make it work the best. It's so important, actually, that there's AI that writes prompts. Of course, there is. And we had quite a range in the class this last summer when I tried it and I asked for what I think 10 titles for assignment one in ES1, and it came back with 10 titles. They were off, meaning they weren't the ones I would have chosen at all. I first conducted the research using Google's advanced search, and then I assigned ChatGPT the same assignment. I was surprised that the differences were quite different. And so was the quality of what it found. So, like I say, it's not intelligent. It doesn't make decisions. It's not guided by any theory. It doesn't recognize theory. So it doesn't know if it's contradicting itself. It might be telling you one thing and telling the opposite thing in the next sentence. These AI models don't know that. So that is why we have to be very skeptical. It's also why we have to learn about this, because that is the key caveat in approaching this is never trust this stuff to the point where you're letting it replace your own capacities to think critically, to discern, to make judgments. Don't ever let AI do that for you because it can't. And when it does, you'll be sorry. So you want to use AI, you don't want to be used by it. And that is my takeaway for you is the more we learn about this, the better. It does have outcomes in terms of our, job potential. It has outcomes in terms of how I teach and how students write essays. So we really do have no choice but to learn how it works. And these two, the one that has knocked my socks off is Notebook LM. It is, I think it's better than ChatGPT by a long shot. ChatGPT is now in its version 5 point something or just 5.0. And this is more of a YouTube gush piece on it's here, yay, yeah, yeah. But then I found one that's satirical. Where did I put that? Is Chat better? And Chat GPT 5.0 better. So there's a lot of debates with people that understand AI and they'll compare products and they tell you this one's great. No, it sucks. That happened with Google's Gemini, where everybody's, oh, Google's Gemini is great. And I don't know if it still exists, but Google, in a sense, has replaced it with Notebook LM. And Notebook LM really is quite astounding. I invite you to see it's only a 13-minute video, well worth seeing. I don't want to project it here, given that it's already posted. So then going back to our where am I? Oh, that is Firefox. Oops. Um, going back to our syllabus. Um, uh, that's the page we just saw. And if you visit the agricanto.org site, which is what that repository is, for ES22, you'll also find the same AI stuff in there. So in fact, if I want to do a share that way, let me go back to home. Oh, I forgot to put a go back home button, and then go to there, and then go to there. Okay, so I'm gonna change the share to, oops, to this one. And this is in Weebly, which is pretty simple web host. All my courses are there. So we go to Environmental Science 22, and this is our class. I have the PDFs for both sections, remote synchronous and remote asynchronous. So they're both here. There are only minor differences in the courses. It's the same course. In fact, I had to let academic affairs know I've uploaded two different syllabi because one is synchronous and one is asynchronous, but they are in fact content-wise identical. The important reason being that in the synchronous class, we actually have a whole series of presentations at the end of the class where students present live their work. If you have an asynchronous class, then those presentations have to be recorded and then shared. So it's the same list here of there's the readings, the two Thomas Kuhn ones, the 5 papers on how to read science papers, and then 4 YouTube videos on Thomas Kuhn, Paradigm Shift, Structure of Scientific Revolutions, and then the next ones is How to Learn Faster with the Feynman Method, and Bibliophile, The Structure of Scientific Revolution, 6 minutes. These are selected to be somewhat short. They're not feature-length films, but this will help us a lot when we get to the Thomas Kuhn part of the course, which is really what goes into our midterm exam. It's one of the only, I would say, I don't want to call it philosophical, theoretical, the only kind of step back view we get in ES22 about science and changes in science is Kuhn's work. Then I have the exact same list of articles with the same videos that are in the AI page. So that they have I have it in more than one place. You can look at it that way. So that is readings in, and these are. Oh, I thought I had fixed these. I did fix these. Why didn't they stick? Oh, see what happens when you paste text that has links in it into Canvas, it drops all the links. You have to go back and do it again. So I might fix this so that you don't run into this problem. The only one that seems to have taken is the one on Notebook LM, which is interesting because yeah, I'm happy with cookies. Why you should start using it right now? Oh, come on, Jesus. Um, and I was convinced that if I really wanted to zero in on using which product would I use most often, right now it would be Notebook LM. I did take a webinar that was organized for faculty um, last spring, and the person who ran the webinar is the one who convinced us, don't think you can tell your students to not use AI in the class. That they're going to use it, so embrace it. It's we don't get to choose no AI. Be nice if we could, but no. And now that doesn't mean that students taking the class, I had this last spring, I had one student who just very much hated AI. He said, I don't want to use it. It's not a requirement of the class. I have to emphasize, it is not a requirement of the class. If you want to do this class the same way we did before we got our elbow deep in AI, it works. You can still get an A in this class without doing the AI thing at all. I'm just suggesting that out of curiosity, we might want to, out of curiosity, um, learn what are the different products, what are they good at. I think you might find that even though you don't want AI to be your substitute teacher or your substitute tutor or your even substitute self, there are some things in AI that will raise your eyebrows. For instance, we have these albums of family photos that go back decades, and they were all taken with good old Kodak film. My mom had a Kodak Instamatic camera, and everywhere when she took pictures. Well, over time, those pictures have faded. They don't look good at all. Some of them even look like they got blurry. There is an AI product that will fix them all. It will restore color, it will restore sharpness, even to photos that were taken 50 years ago. There's AI that will fix audio where you've recorded something, but the microphone was too far away, or there was static, or there was background noise in the room, and the audio quality is so bad you can't share it. There's an AI product, and it's free, that will um, clean up an audio track that needs cleaning up. So it's not just text research and writing that AI does, obviously. It does things like Notebook LM does podcasts, it does videos, it does animations, and that's what makes it so interesting. I will restore these links, note to self, restore syllabus links. I don't know why Zoom deleted them. And this is, of course, we have Students for Disabilities Office, and I do get requests from when the student works through that office and they have special requirements. For example, they might need longer time to do an exam. That's the most common one. In Canvas, that's really easy to do. I just go in and change the amount of time allocated to that one student. So sometimes it's time and a half. If the exam is 2 hours, they might need three. Um, and then there's the phone numbers to call. Assignments. This is pretty straightforward. All of our quizzes and exams and reading scientific papers is 40% of the grade. The slideshow presentation and write-up is 60% of the grade. That is the final exam. That is what you could call the money shot. Now it does say and write-up, which includes the previous before you actually assemble your presentation in PowerPoint. There's the third assignment has you prepare for how to do that. So that's why we dedicate a good chunk of time in the course to this part of the course. And I think when you see the syllabus, it's actually about 6 to 7 weeks. So this tells you a little bit about the presentations. And for the synchronous class, I've had students ask the question, well, um, what if I'm really shy and I can't do it live? I just freeze up. And that some people really that really is a serious thing. I just saw a whole article on that on people who are very distressed by public speaking. So she said, "Can I record my presentation?" And yes, you can. So she basically used a Zoom or she used something like that, lined up her PowerPoint presentation, and then she just did a voiceover while she was showing it, and it worked fine. So you aren't obligated to do it live if you don't want to. The advantage, of course, in doing it live is that you're much more conscious of the pace that you're moving, or move to the next slide, or whoops, you're stuck on a slide, you meant to move to the next one. Um, and the advantage of recording it is that you can edit it and go back and say, I need to do that part again. So each one has its advantages. I like the live one because it gets us used to public speaking, and we'll in fact spend a little bit of time in this course on the challenges of public speaking that have nothing to do with the content of the class as far as science goes, but it does have to do with your education to the extent that I think it's going to happen more and more. That to the extent that AI is able to produce text and that that text can be pretend that it's done by a person, then the option in education is to have students present their work orally, where there's no AI. I went to a meeting just last week. It was 5 hours. It was a 5 hour webinar for faculty on AI in the classroom, and we had fantastic presentations. By the way, our student trustee, oh my, her name is Frances. It's a French sounding name. She's incredible. She is incredible. She's a brilliant person. And she learned us all up. What she did was she took a step back from we were all like in the weeds, right? I'm going to talk about ChatGPT and how I use it in my class. Everybody was saying how they were using different products in their class and how great it was. And she did a step back and said, well, we have to really ask the question, what's happening socially? What is the philosophical change happening? What's happening with pedagogy? What's happening with trust? Brilliant. It was brilliant. No wonder she's a trustee. There is a financial aid office. If we had a textbook, you could go there for financial support for purchasing a textbook. Th This is interesting, plagiarism. Well, AI makes plagiarism really, really easy. So in a way, the word is now a little bit outdated. It's bigger. It used to be passing off someone else's work as your own was plagiarism. Pretty straightforward. In fact, the library had a little flyer. What constitutes plagiarism? Different kinds of plagiarism. Are you plagiarizing yourself? Which, by the way, some faculty members in universities do. They take an old paper they wrote, published years ago, they redo it and publish it again. It's called shingling. It's also called self-plagiarism. So it's something you never want to be caught doing in higher education. And it does, in fact, it can really ruin your career in graduate school. It can actually get you denied tenure as a professor. So it's a serious thing. But with AI, it's harder to detect. And so you need AI to detect AI. And even then, it's not that good. The folks at Turnitin, where we used to upload term papers, we had a webinar where they said, "Oh no, now we've equipped Turnitin with AI detection, and it'll detect AI." But no, it doesn't. It's been tested by neutral third parties, and they say this claim by Turnitin that it detects AI is really outdated. AI has gotten so much better that the typical little pitfalls that you used to see in terms of language choice, turns of a phrase, etc., you can tell, for example, Notebook LM, please write this paper at a sixth grade level. And then it rewrites it at a sixth grade level. So challenged we are. And then here's the week-to-week syllabus. So we do start on the 3rd of September, and what you're seeing now is introduction to the course. And then we'll talk about science methods and hoaxes. That's going to be what follows after. And then AI, it's a bit out of order because we're talking about AI now, right after the introduction. So that is the week to week thing. This I probably because it's easy to edit. If there are changes and I anticipate changes, then we'll do that. So you can see our midterm happens in October, October 22nd, and it's when oh, it's oops, this is wrong. It's published on the 15th and it's due on the 22nd. There you go, another mistake. And it's of course it's online, and it's not it's I want to say it's open book, open notes. In a way, it is. It's also a really simple midterm, but it's not multiple choice or true false. You actually have to write very small amounts of text in a little text box. And most of it is about Thomas Kuhn and the nature structure of scientific revolutions. But I have to add a few more questions to make sure that we're meeting our SLO. So that one is subject to some change, but it's not long. I kid you not when I say it's like 10 questions. Um, Then we talk about how to assemble your PowerPoint. I use that as sort of symbolically speaking. It doesn't have to be Microsoft PowerPoint. It can be other, it can be Google Slides, it can be Apple Keynote, whatever. Um, so this is where I share with you how I assess the presentations. And this is when assignment 3 is due. This is the write-up part, in a sense, of assignment 4, which is the presentation itself. So together they make up 60% of the grade. That's why you really want to take seriously the selection of the science paper that you and make sure it's one you like, because you're going to be with that paper for quite a while. And then this is all the time I've set aside for presentations. And what I'm doing here is to make sure that we get 3, but 4 is pushing it. I'd like to have 3 a day, or, 3 a week. So with this structure, we definitely fit 3 a week, and everybody gets to present. If we have to squeeze in one more and make it 4, that's okay, but definitely not 5. Even though the presentations are only 20 minutes long, and that's your sort of your yardstick, you want to fit it in 20 minutes. We still always want time for Q&A. And we also want time at the beginning to sort of assemble ourselves. So there's wiggle room in it, and that's intentional, because the last thing I want is to have 5 of them and to have students stressed out. They're looking at the clock, they're running out of time, and I have to blow the whistle when their 20 minutes are up. No, we don't want to do that. That just ruins the whole purpose of the assignment. The assignment is that you're going to be comfortable with this. You're going to be able to speak with authority to the subject you chose. You know the paper inside out, almost like you wrote it. And you're teaching us all what you learned about. So that's why I'd like to leave. These are all 3-hour sessions. I want to make sure that students get at least half an hour, 20 minutes for presentation, 10 minutes for Q&A, or more. If it's 3, it all fits. So that is the syllabus. I'm showing it here as the editor done. I should have turned on the student view so that it wouldn't be. Let me see if I view as a student. There we go. This is how you see it. So it's the same, um, same comments, same links. So the links I want to fix are the ones that are up here with the papers, wherever they were, that didn't match these, the AI papers. And what else? And then there will be changes and adjustments made to the week to week, depending on what we get covered and what we don't get covered. So going into the modules and publish them as we go along, because I have to make alterations. For example, here's week 1, and there's just the interesting one about it's by the time we get to this, you'll know what it's about. And then ES22, what is the week 1 content, and it takes you to our page on Weebly, and this is like horribly out of date. Um, so and I need to update them. And as I update them, I publish more and more elements of what is in each module. So right now, what I've left is the readings and the links to videos, etc. What is missing, what is not published at the very top, is a recording of the lecture and related documents. The district or valley also puts this at the beginning, of course, of our modules, and they walk you through all these services and resources, the welcome letter, etc. I think I preserved the one that's most up to date, because suddenly my Canvas shell was full of them from previous years. So that is in modules. Announcements, I will make these um, as we go through. And I think since I've published the class already, you might have already seen both of these, or this one might show up on Wednesday morning. And there is the link that we use every week to access the class. So you always want to check announcements. That's the only way I have of communicating with you on changes, if there's anything that you need to know, deadlines, et cetera, et cetera, et cetera. That's in announcements. If you hit home, it'll take you to syllabus. I've made those the same thing. And then there is the discussion of assignments. So you'll see that there's 4 of them, right? There's finding a science paper, then there's writing up a short summary of the one you chose, and then marking up the science paper and uploading the markup, and then your PowerPoint presentation. So there's 4 assignments. Now, I did think of breaking up assignment three into two parts, but a lot of what's in two is really a summation, almost an abstract of the one you chose when you went through this process, and that is finding the science paper. Um, that's assignment land. And then maybe in quizzes, I don't know if it's published yet. It might, yeah, midterm exam. Here's the 6 questions, but I think I have to add 4 more to make it the right SLO. So that would be for the midterm, and it isn't until October. So it's a ways down the pike. So let me get out of student view and stop the share. Voila. And then see if I have my ducks in a row for what follows here, which is now we're going to get into a series of small videos on the scientific method. And I hope also by the time we get to the end of it, we will have covered the burning question. Let me see what I had put in the syllabus or yeah, in the syllabus. What was the burning question? There's AI, there was hoaxes, some hoaxes in science. Maybe if we can't get to those, I might have moved them into next week. But they're worth seeing because it shows you how um, fake science or that something that kind of looks sciencey, what Stephen Colbert used to call truthy. It seems truthy, and it's not. So that is what will happen that week. So with that, let me stop the recording or pause.
We're going to discuss, what is science? What is science? And then we're going to progress into the scientific method, the steps that are used to collect information. So let's go ahead and get started. What is science and what is the scientific method? All right, so what is science? Well, a very vague definition of science is that it's a process that produces information about the natural world. And I do want to stress the phrase the natural world, because there's kind of a argument going on about should we allow the supernatural into science, and that's an argument we're not going to pick up in this video. But currently, absolutely, we only look at the natural world. We don't allow the supernatural to explain the natural process. One thing about science is that it's supposed to be objective, and that can be very hard for people because we often come into an experience with a bias. We come into an experience with a preconceived idea of what we think is the answer, and people don't usually like to be wrong. And so that's one of the harder parts of science, is to look at something objectively, to come in with a fair and balanced expectation. If you come in with a bias, well, that bias might weigh you down and kind of force you to ignore the reality. That's one of the harder parts of science, which is the reason why in science you, of course, share your results with others. In case you do have a bias, hopefully your bias will be uncovered by someone else. One thing about science is it needs to be repeatable. I just brought up that often science experiments and data learned are published in journals and shared around the world. Well, that's so others can repeat their experiments to see whether or not the idea is correct. One thing about science is that there are certain tools and skills that are used to gather information. And probably one of the more obvious ones is the skill of observation. Here we have people doing microscope observations, trying to uncover more secrets of the microscopic world. Here we have just pretty much just the opposite, using a telescope to peer into the nighttime sky and uncover secrets of the universe. In this case, we have a picture of one of the Voyager probes that was launched in the 1970s. And these things have been drifting around in our solar system and now beyond since the 1970s. And they've observed the solar system and sent back to Earth the data that's been collected. So there's all kinds of observations that can be done. And let's not forget one of the more famous observations. Here we have a little drawing of Isaac Newton, and an apple just bumps him on the head, and that observation of a falling apple led him to uncover this force in nature called gravity. Well, another skill, another tool that is used in science is simply experimentation. And in our picture here, we have a young lady doing an experiment on DNA electrophoresis and using electricity to separate small bits of DNA so that those pieces of DNA can be analyzed. In this pretty famous experiment that took place in 1928, a gentleman by the name of Frederick Griffith taught us that bacteria can transfer genetic information. In the picture, he injected mice with a non-deadly bacteria, and no shocker, the mouse lived. Well, he then injected mice with a deadly bacteria, and no surprise, the mice died. Well, he then injected the mice with the deadly bacteria, but before he injected them, he heated the bacteria and thought that that would kill the bacteria. And he was right. The bacteria was killed, so the mouse lived. The mouse was not harmed. And here's where it gets interesting. He then had a mixture of non-deadly bacteria mixed together with the deadly bacteria that had been heated. He was expecting the mice to live, but was surprised to see that they died. He figured out that bacteria, the deadly bacteria that had been heated, they have DNA in them. That DNA was transferred to the non-deadly bacteria that were still alive. The non-deadly bacteria became deadly. And we learned that bacteria, through this experiment, that bacteria can transfer genetic information. And this also taught us that DNA is the genetic material. This was at a time where we weren't quite sure. And so ultimately, data is going to be gathered by what we call the scientific method. Now, we're going to go through the scientific method in more detail. So let's move on to that now. So here we have the scientific method. Very general definition of the scientific method. It's a series of steps that we use to collect information and to solve problems. And it begins with number one, asking a question or identifying a problem or making an observation. So we're going to go through a fictional example of this in just a moment. But once you identified a problem, that leads to creating a hypothesis. So constructing a hypothesis, which is just an early answer. A hypothesis is what you think the answer is to the problem that you've just witnessed. After you have what you think is the answer, that's called the hypothesis, then it's time to actually do the experiment. The experiment is going to produce you data. That data, of course, has to be analyzed. And then once you've analyzed the data, you can draw a conclusion. Does your conclusion support what you originally thought? Does your conclusion support your hypothesis? Follow the arrows there. If your conclusion does support the hypothesis, well, then you still got to repeat the experiment, repeat it, perform the experiment again, if it's possible to perform the experiment again. And then what about the other side? Well, what if your data is not supportive of your hypothesis? Well, then you kind of go back to the beginning and you construct a new hypothesis and you kind of start all over. This right here is the scientific method. Let's go through the scientific method using a fictional example. Okay, let's actually look at the first two steps of the scientific method on this one slide here. Step one is observation or identifying a problem. And in our animation, we have a young lady laying in bed with headphones on, listening to music. So the reason I have this animation, and this animation is going to kind of be the basis of this video here for the rest of the video. In our example, in our pretend fictional example, maybe she makes an observation. Maybe she accidentally fell asleep listening to music a few times and she seemed to sleep better through the night. So that's her observation is, I seem to sleep better when I play relaxing music throughout the night. And maybe she's sleeping better because of the music. Maybe it's some other factor, but that's just something that she noticed. That's a problem that she noticed. So then step two is write a hypothesis, create a hypothesis. Typically, what we're going to show you is it's an if-then statement. And an example of this might be, if there's relaxing music playing, then I will sleep longer. You might often see if, then, because. If there is relaxing music playing, then I will sleep better because the music puts me in a calming state where I'm able to relax and sleep better. So that's what we mean by an if-then statement. And that's generally created step two in our hypothesis. Well, let's move on to the next step. Okay, so now we move on to the actual fun experimental part of the scientific method. And this is where we actually design an experiment. And when we design an experiment, what we're going to see is that there are two parts to an experiment, two groups. The first group is what we call the control group. And what's so special about the control group? Nothing, literally nothing. The control group is the group of test subjects that receives no special treatment. The purpose of the control group is we're going to use it as a comparison. Well, what are we comparing it to? We're comparing it to the second part of an experiment called the experimental group. And notice from the picture here, the picture on the left, picture on the right, they're exactly the same because the control group, the experimental group, you set them up exactly the same, but with one little difference. In our animation, there she is listening to music. There's that one little difference. The one little difference between the control group and the experimental group is what we call the independent variable. It's the one factor that's different. All other factors are supposed to be the same, except for what we call the independent variable. The independent variable is the factor that we're testing. In this fictional study here, we're testing whether or not music affects our ability to sleep. Well, during the course of this experiment, maybe she records herself for a month, records the amount of sleep that she gets for a month with music and the amount of sleep she gets for a month without music. Well, that's going to generate data, and we call that data the dependent variable. And I hope you see why it's called the dependent variable, because the amount of sleep she gets, which is the dependent variable, is that can be recorded. The amount of sleep that she gets depends on whether or not she listens to music. So I hope you see why it's called the dependent variable. So anytime you're gathering data in a science experiment, maybe you're measuring the heart rate of people, maybe you're measuring the blood pressure of people. Anytime you're measuring something numerical, that's going to be your dependent variable. Let's move on to this situation in a little more detail. Okay, so let's look at the control group versus the experimental group in a little more detail here. Here we have our experimental group, and we have the same person maybe recording the amount of sleep that she gets over the course of 1 month. So she's kind of going to set up two experiments here. And during her 1 month of recording her sleep, she's also exercising regularly. And during the 1 month where she's recording her sleep and exercising, she's also eating very similar meals in this 1 month period. You know, well-balanced meals of good balance of carbohydrates and proteins and lipids. And the one difference is, if you just notice, we added earphones with music. So the one difference between the control and the experimental group is in the fact that she's listening to music. All other factors are the same in this case. So let's pretend that after 1 month of recording her sleep, she's averaging about 6.2 hours of continuous sleep every night. And pretend that for 1 month while she's recording her sleep, she averages 7.5 hours of sleep per night when she's listening to the music. Well, something had to cause that extra sleep. And so, by the way, that the data that we just collected is what we call the dependent variable. And I hope you see why it's called the dependent variable. The sleep depends on, and that's why it's called the dependent variable. The sleep, the amount of sleep depended on whether or not she listened to music. And so if I were to ask you, okay, examine the data. Does the data support the original hypothesis that this woman had? I hope you would say yes. Since all other factors are the same, the music must have caused the extra sleep. So granted, this is very much a simplified experiment here. If this was to be done for real, yes, there are other factors you would have to control besides just exercise and food. I'm just kind of using this to hopefully illustrate a point. Let's move on. Okay, let's move on. Let's try this situation. Again, let's pretend it's kind of the same situation. Let's say the lady's going to record her hours of sleep for a month. And so in the control group on the left, no music. The experimental group on the right, she's listening to music while she sleeps. And notice how during the day for 1 month, however, they're doing different exercises for that 1 month period. Also, the woman's eating different meals during that 1 month period where she's recording her sleep. Well, if I were to show you that this data right here, pretend that the control group on the left, she slept continuously for 6 hours, and the experimental group on the right continuously for 8 hours. If I were to ask you, does the data support this original hypothesis? I hope you see something very different in this situation. In this situation, we can't say yes or no. Does the data support the hypothesis? We don't know. The data would be considered invalid, and I hope you see a reason why. There are too many variables in this experiment. She has the intended variable, independent variable of sleeping with music and sleeping with no music. There's a second variable with different amounts of exercise, and there's a third variable with changing the food. These are all possible factors that could possibly explain why the woman received an extra 2 hours of continuous sleep. So when you have more than one variable, you really can't pinpoint your explanation. There's other possible explanations. That's the importance of having only one independent variable in an experiment. Okay, so here's a little practice story problem. It says the United States military wants to see if soldiers with only 4 hours of sleep can operate at the same level as those who normally get 7 hours of sleep. 100 soldiers are allowed to sleep 4 hours a night, and another 100 are allowed to sleep for 7 hours a night. During the day, the soldiers are tested for their marksmanship on the firing range. Well, go ahead and pause the video and try to answer these 4 blanks. I'm going to go over the answers in 3, 2, 1. So for naming the
Yeah. Okay. So let's see. Let's see if we can do this one and get it right. It's not too complicated. Let's see. What is the control group? Anybody, you can just unmute yourself and holler which one you think is the control group.
The soldiers.
Well, they are the subjects of the experiment, but
Oh,
if
I
we're-
see. Go ahead, Professor. Sorry.
go ahead. Which do you think is the control group? What is the control? It's something that doesn't change, right? So if control is something that doesn't change, that would be the soldiers that were allowed to sleep 7 hours at night. That's supposedly their normal sleep. The experimental group, you can unmute yourself and identify which would be the experimental group.
The ones that are sleeping only 4 hours.
Right. Because that's what we're experimenting on, right? So the experimental group is the 4 hours. What is the independent variable?
Depending
Now
on the
remember,
person.
the independent variable, what was the answer?
I said it depends on the person of how they reacted. The one with the 4 hours sleep depends how you reacted to that, and the one with 7 hours of sleep depends on how
Yeah.
that.
So, but if we want to identify, remember the independent variable is the one that would apply to. I'm going to venture here and say that the independent variable would be sleep, just writ large, both the 4 hours and the 7 hours. And then what would be the dependent variable? What are they being tested on?
Their marksmanship.
Marksmanship. So the dependent variable would be the results. In other words, how good are they at the firing range? Now, let's see if I got this right. I'm not sure I got right independent variable, but let's see what the answer is.
Group, I hope you said, well, that's the soldiers that get 7 hours sleep. But
Yeah.
The control group is the group that gets the normal. And in the story, it says normally get 7 hours of sleep. That means the experimental group are the soldiers that are only getting 4 hours sleep. The experimental group is the group that we alter. It's the group that we're changing.
Right.
And what we're changing is the amount of sleep. And so that actually answers my independent variable question. What's different between the two groups of soldiers?
amount of
is the
sleep.
amount of sleep that
I
they're
said
getting.
sleep writ large, but
Exactly.
amount of sleep. Okay,
Variable.
good point.
What's the dependent variable? What's being measured is the score on the firing range.
Okay.
So this little story here, I have a few other stories.
Okay.
So let's practice.
All
Here we
right.
go to the next one.
All right, next one.
Okay, so here we have a farmer with 2 bags of fertilizer, and the story says this farmer wants to test a new fertilizer on his crops. So he sections off 2 large areas of his field. In section A, he waters his crops as usual and uses his normal fertilizer called Grow Right. In section B, he waters his crops as usual, but adds a new experimental fertilizer called Evergrow. So after one growing season, he records the growth of the crops. Well, go ahead and pause the video and try to answer these 4 blanks. Go ahead and pause the video. I'm going to show the answers in 3, 2, 1.
All righty then. So the control group. No, there's 2 different fertilizers here. So this farmer is experimenting with a new one. Which would be the control group?
The normal one.
The normal one, right? The one that he's always used. Then what is the experimental group?
The new one.
The new one, the Evergrow. So the control group is the Grow Right. The experimental group is Evergrow. What is the independent variable?
The fertilizer.
And there's fertilizers in both. That's a good one. Okay, fertilizer is the independent group because it talks about watering, and it doesn't say that they're different crops. So we're assuming that it's the same crop. And then what would the dependent variable be?
The result of the growth.
The result of the one that's called Evergrow. Okay, let's see if we got the one that always catches me is the independent variable. So let's see what the answer is.
So for naming the control group, I hope you would say, oh, that was section A. Those are the crops that were given Grow Right, because the control group is the group that receives the normal. And in this case, he's always been using Grow Right. The experimental group would be section B, the crops that were given this new factor called Evergrow fertilizer. So that's the experimental group. So the independent variable, if you recall, it's just the difference. What's different between section A and section B?
Oh, type.
It's the type of
Type.
fertilizer.
We're close. We were saying the fertilizer. Okay.
Lastly, the dependent variable is the data measured. How does he know which fertilizer works better? He has to record and measure something. And what he's doing is recording the growth of the crops.
So we got it
another
wrong.
example.
Okay. We got that wrong. The dependent variable is the growth of the, after all, it is fertilizer. I thought the dependent variable would be, would actually be the answer, section B, crops given Evergrow. So
I said the result of the growth.
results. So Chris, you got it right. I got it wrong. Okay. Let's go to they get a little trickier. There's 2 more, and they get a little trickier. Well, you'll see.
So here is another example. Here we have a young student, and he wants to know if his new study method is more successful than his traditional study method. So for 1 month, he studies for his classes using his traditional study method. The next month, he studies for his classes using this new, maybe better study method. He's not sure if it's better yet. And so at the end of this testing period, he simply compares his grades. So just like the other examples, pause the video, try to answer these 4 blanks. I'm going to go over the answers in 3, 2, 1.
Okay. The control group. Well, this one might be pretty straightforward to a point. But let's see, what is the control group?
The traditional study method.
Traditional study method. And then the experimental group,
It's the new study method.
the new study method. And here's that, name the independent variable.
The amount of time, could it be?
Amount of time.
Or the frequency, how frequent he used both study methods?
Oh, well, actually, it says that the next month. So there's 2 different months. That's a good point you're raising. There's 2 different months. So the first month he's doing the traditional one. The next month he's doing the new one. So would the independent variable be time, or would it just be study? With the dependent variable being at the end, the grades. See, once again, George could get this wrong, but there's also an interesting assumption in this one, which I'll mention when he's done explicating. Okay, fire away.
So for naming the control group, I hope you said that's the 1 month where he was doing traditional studying. So maybe he was making flashcards and outlining his textbook, whatever his traditional study method is. The experimental group, that would be the 1 month where he was experimenting with a new study resource. Maybe he was doing online tutorials and online simulations. So I hope you see the difference right there between the control and the experimental group.
Okay.
So it says name the independent variable. What's different between those two groups? The difference is the study method.
The study, okay.
That's what we
Yeah.
call the independent variable. It's the difference between the control and the experimental group. And how does he know if this new experimental method worked? What data is he collecting? He's comparing and collecting his grades. Again, granted, if this was an actual science experiment, yes, there would need to be more variables that are controlled, but I hope you see the point that I'm.
Well, I do see the point, but this one has an assumption in it that might really screw up the whole experiment, because he's taking a class and it looks to me like it's a math class. And I was not a genius at math, but what I remember in math classes is that the first, few weeks, maybe the first month, you're kind of reviewing and adding to the previous, let's say it's math 2, math 3, right? So when you start math 3, the first few weeks, you're reviewing math 2, and then the material gets harder. So the assumption here is that each month is the same, that they're interchangeable. But I think that the second month is going to be harder than the first month, because that's how classes go. So in fact, he won't be able to know if he only did his study method with the second month of the class, because that might, if he gets better grades that way, then he knows that the harder part of the course was that he did better on it because of his new study method. But that one is tricky. And he pointed out, okay, there are a few assumptions in here that, we would probably have to alter. Then let's go to the next one, which I think is near and dear to our hearts.
Okay, here's the last example. Pretend that the city of Los Angeles wants to know if there's a connection between physical fitness and air pollution. 50 volunteers from the mayor's office agree to be tested. First, they're asked to ride a stationary bike for 1 hour in a pollution-free air chamber. A week later, the volunteers return and are again asked to ride a stationary bike for 1 hour in a chamber filled with air pollutants common to Los Angeles. Their heart rates are monitored throughout this 1 hour bike ride. Pause the video and try to answer those 4 blanks at the bottom. I'm going to show the answers in 3, 2, 1.
Okay. What is the control group?
Pollution-free air chamber.
The control, which chamber? Sorry, repeat.
The free one, like no pollution.
Oh,
The room with no pollution.
the room with no pollution.
Yeah.
Okay, but remember what the purpose of the experiment is, to see if there's a connection between physical fitness and air pollution. So if air pollution is normal in LA, means we're breathing it all the time, then wouldn't that be the control? The exception would be the room that's kind of clean. I mean, that's had the air cleaned. So I'm going to venture to say the control group is actually good old LA smog. So it would be the room that is it's filled with air pollutants common in Los Angeles. Then the experimental group, I think, would be the room that's clean, so that we'd be seeing what are the difference in heart rates with these 2 different bike rides, and the real significant one is going to be the clean air, because you're testing for pollution. The independent variable, that might, the independent variable. Anybody venture the independent variable?
The environment, because one is in a room without the pollution, and then the other one
With
is
the pollution?
being filled with the pollutants. Mhm.
Okay, so let's say the independent variable is, in fact, I guess, breathable air, something like that. And then what would be the dependent variable?
The time, because the time is not changing. They're both riding the bike for an hour.
But remember that what they want to do is to see if there's, they're measuring physical fitness with heart rate. So the dependent variable would be the data gathered from from reading the heart rates in the two different examples. So let's see if Letty got independent wrong again, because I seem to be good at getting that one wrong. Let's see.
Okay, so this one might have been a little tricky. The control group are the people who breathe the polluted air.
Right.
And at first that kind of seems backwards, but then we realize, well, because the control group is the group that receives the normal. And in Los Angeles, it's normal to breathe polluted air. Los Angeles is always either top 3 in the nation as far as most polluted air. For the experimental group, what's different is the volunteers who breathe clean air. So that's our factor right there, because again, clean is not the normal. And so that makes the breathing the clean air something different. That makes it the experimental group. Name the independent variable. I hope you said, well, the quality of the air that is being breathed is the independent variable. That's what's different between the control and the experimental group. And the data recorded, the dependent variable, the data recorded, it's their heart rate as they pedal on the stationary bikes. So I hope these examples help. Let's move on.
They do, actually, because it can be tricky.
Okay, so let's
here's
get back to the steps of the scientific method. The 4th step is what we call data analysis. And it says data from the control group is compared to the experimental group. In the graph, you can see the data. The data that we said a few moments ago was that the control group without music got about 6.2 hours of sleep per night, and the experimental group with music got about 7.5 hours of sleep per night. So there's the data side by side in a nice readable graph we're comparing the two. And you can hopefully see that, we mentioned this a few moments ago, that the data seems to support the earlier hypothesis. Now, one thing I want to mention is that the hypothesis will either be supported or rejected by the experiment. It's not going to be proven. So I hope you're not going to look at this data and say that it's proven that music gives extra sleep. It's not proven at this point. It's supported at this point, yes. But by no means are we going to call it proven. It hasn't been repeated and retested by others. So we're
very important in peer review and the reproduction of experimental results. So there's not enough data here to call it proven. And that's why you often see scientists will hold a press conference or announce something, and they're very careful with their language. For example, they'll sometimes say, we're approaching this with what's the term they like to use? Significant confidence. We find the correlation compelling. We find this to be indicating the need for more research. They never say we're 100% sure. Even when they are close to 100% sure, they'll still say we're 99% sure. Because in science, you're never 100% sure, because you don't know what you don't know, and you don't know where you might have gone wrong, even in the conventional or the normal way of conducting experimentation and the reading of results. One thing I want to point out to in this one, and notice that in this one, there's a nice little column, or whatever we call these kind of graphs. It's a bar graph, but it's a 3D bar graph that has the two different pieces of data. When you select your science paper for your presentation, you hopefully will pick one that has good graphics when it comes to quantitative data. In other words, where it has stuff like this and not a table. Now, in previous classes, what we've done is we've learned how to import those tables into Excel and then use Excel to generate these kinds of graphs. But what I'm seeing in what we've talked about today, that AI will do it also. AI will produce graphics from quantitative data. So I'm curious there. I mean, I find Excel does it very quickly. So I don't know if I have to go ask a chatbot, to compare two pieces of data, but you can see how much easier it is to read visual representation than it is to read numbers. Here you can really see the distance or the difference between 6.2 and 7.5. It's visually clear, even on the scale in the background that goes from 6 to 8. But if it was on a table, then it wouldn't have the scale. It would just have the time, and with music, without music, and it would be a boring little columns and rows, right? So that's why tables are often not a good idea in a science paper, because you're asking the reader to go out of their way to interpret the table, to find the biggest number, the smallest number, the average number. And if you could just do this, it's so much easier. Let's see how he ends this one.
I'm going to call it proven yet. Let's move on. And then we have the fifth step, the conclusion. So in this step, like it says, your findings could be shared and repeated by others. A second experiment, a third experiment could be designed by others. Not necessarily using the same lady, but the point is that others would have to repeat this, or perhaps even the person who originally designed this experiment could repeat it themselves. But that information, that experiment would then be shared by others, so then they could also repeat it as well. And over time, perhaps, just perhaps, and I'm not saying this happens in a month or a year, it could take decades perhaps, but over time, a hypothesis could eventually become a theory. A theory develops over time. You know, in the picture, we have kind of a picture just summarizing Darwin's idea of natural selection. Today, Darwin's idea of natural selection is very much a well-established, accepted scientific theory. But in 1859, when he wrote the book on the origin of species, this was really his hypothesis at the time, that organisms with advantages would survive better and pass on those advantages to their offspring. And so hypotheses, if given are able to stand the test of time and intense scrutiny, eventually could develop into what's called a theory. Well, both theories and both hypotheses will change and can change based on new information. There might be new information that completely redesigns how we view natural selection. Maybe not. It's been 150 years of people trying very vigorously to discredit and disprove natural selection, and they haven't been successful. So natural selection looks like a very strong scientific theory.
Yes, it has really resisted the test of time. I mentioned to you earlier that when Darwin was asked, well, what's the mechanism of inheritance? He said, I don't know. Someday we'll know. And it took, a long time to find out the mechanism was DNA. But in the 19th century, people had no idea what DNA was. The other thing is that Darwin was very influenced by the sort of, it's hard to call it philosophical, kind of the ways people thought in the 19th century. By people, I mean, scientists and philosophers and so on. And their idea, their belief when it came to science was that change is gradual, that it happens in small increments of time, sometimes even invisible to human witnesses because our lives are shorter and we're used to moving things fast. So we don't see it. We don't see changes on the land. We don't see geomorphology. We don't see tectonic uplift, things that are, according to all those different sciences, gradual, little pieces at a time. However, there has been a testing of Darwin's belief that all evolution is gradual. It's called gradualism. And it was very popular in the 19th century. For example, Karl Marx, who was a 19th century philosopher and economist, thought that social change was gradual unless there was some kind of upheaval, like 1848, the French Paris Commune or stuff like that. So gradualism influenced a lot of social science and economics and natural sciences in the 19th century. Into the 20th century, one of the things, of course, was the discovery of the mechanism of inheritance, DNA, but also that, in fact, Darwin was probably not right about these changes happening gradually. Now, it would be true in terms of the ancestor finch and then the three speciated species from that common ancestor, and that would have taken possibly tens of thousands of years. So it's not like Darwin was wrong, but there is a little finding that has kind of, it hasn't thrown a wrench into the works, which is what makes Darwin's evolutionary theory so useful, is that even when it's subjected to new findings, it's still there. It won't go away. So this is the one. There was in Soviet Russia a long time ago, they were raising foxes for their fur, for pelts. And it was a farm that was like way out there in Siberia somewhere, where they would raise these foxes for their fur. And foxes, being wild animals, could be pretty aggressive when they grew older, when they grew to be adults. So the people handling them would, get bitten, and they'd have to wear these big protective gloves. And the foxes were, of course, miserable in their little cages. So they asked a geneticist, or they asked an expert from Moscow to come over and see if he could breed the aggression out of the foxes. His name was Gyayev. Gyayev goes to this fox farm, and does something that seems very intuitive. And what he did was he would stick his hand into the cages. If the fox attacked his hand, he would withdraw it, and then he would not breed that fox. Then he would stick it in another one. If the fox was more docile, less aggressive, then he would breed that fox. So he selected from all the foxes on the farm the least aggressive ones and bred those, and kept the ones that were most aggressive from breeding. And in a very short time, the ones that were selected by humans because of their less aggressive characteristics went through phenomenal change in a short period of time. I mean, it's astounding how quickly. One of the things is that they started barking like dogs, which foxes don't do. The other thing is that their coats changed color. Their coats became more like dog coats, grow more varied, more colorful, not just the old fox color. And in some cases, they would even respond to their names. They became like dogs. And it happened in like the blink of an eye. So Yalev's breeding the aggression out of these foxes, which then they became pets. In fact, there's a whole, I just saw in the New York, there's a whole industry of people who have foxes as pets. I don't know if it's legal in every state, but there is such a thing as a docile fox. There's lots of YouTube videos about that. So what it was is then some evolutionary leaps. For example, the domestication of dogs from wolves maybe did not take thousands of years. Maybe it happened in the blink of an eye. And that is, in that sense, it doesn't stand Darwin's theory on its head. It just says, yes, you're right. A lot of change, a lot of evolutionary change is gradual, takes thousands of years because it has to do with mutation and natural selection. And those are the two mechanisms that Darwin argues are the mechanism for evolution: mutation and natural selection. And mutations are always happening constantly. So most mutations are not selected for, meaning that the individuals within a community or a species that have that mutation are often selected against, so that it's not an advantage. It's only when a mutation represents some kind of advantage, and then that particular individual has breeding advantages, that then the trait is passed on to future generations for that particular species or community of animals, etc. So that is a big difference between gradualism and what you might say, very quick, what's called punctuated equilibrium, meaning that Stephen Jay Gould writes about this when he interprets, the misuses of Darwin and the misunderstandings of Darwin vis-a-vis how he understands evolutionary biology. And he's a big defender, he's passed away, big defender of evolutionary biology and Charles Darwin. But he points out that Darwin was a gradualist, and that what we really see is that evolution happens in fits and starts. It's not steady like the erosion of a mountain. It happens in quickly, and then there's relative equilibrium, and then another event. And the same is true in physical geography. In geomorphology, there's tension between the gradualists that say the changes on the land are almost invisible and slow, and the catastrophists that say, no, there's catastrophes. There's tsunamis, there's earthquakes, there's fires, there's all kinds of things that will change a landscape in a matter of days. So both things are true. The changes on the land are, in fact, gradual, but they can be catastrophic. They can be quite eye-opening, like what we've seen here in LA, with all these fires. And we're also very conscious of earthquakes, for instance. So let's see if I can close this one. I have one more to share with you that remembers. Does it remember? Yes, there it is. And this one is very interesting because it points out something that I hope is also a takeaway in this class, which is that we are normally, I don't want to say normally, but we're led to believe that the scientific method and advancements in science and so on are something that is almost uniquely European and Western. That the ancient Greeks and Aristotle and all this stuff, and reason and all the way to all of the different scientists that made up the scientific method and scientific discovery. But it isn't true. The scientific curiosity is universal. Human beings are naturally curious, and because humans are very good at observation, very good at it, it leads humans to ask questions about what they've observed over time. So that those first two steps or first three steps of the scientific method, an observation, then a question, and then a hypothesis that answers the question. And that would be true of a lot of civilizations in the world. In fact, I would say even non-sedentary people, even people that are nomadic to some extent, also have scientific knowledge. They have knowledge of plants, they have knowledge of animals, they have knowledge of seasons, they have knowledge of the stars, and they pass this knowledge on culturally to the next generation. So it's usually embedded or in some way encoded in a belief system or in a mythology or in a religion. In other words, it isn't presented as lab coat science, but the findings, the usefulness of the knowledge is that it is scientific. So that's why humans were able to domesticate plants. All of the great plant domestications are done by experimentation, by selecting. When you consider that maize or corn that is now universal food, but it was invented in Mesoamerica. Mesoamerica is sort of central Mexico all the way down to Central America, which was really the birthplace of maize, of corn, what Americans call corn. In other countries, they call it maize. So that's an interesting distinction. But it took a while to take a wild grass called teotzintle and to breed it so that the ones with the biggest tassels are selected for, the ones with the small tassels are not, until you get the full mazorca, the full corn cob, which is now one of the most nutritious foods in the world. And it was the basis of 5 civilizations in Mesoamerica: the Toltecs, the Olmecs, the Aztecs, the Mayans. They were all the corn cultures, and then it diffused from Mesoamerica to the Andean countries and to North America. So North American indigenous people also grew corn, and Andean people grew corn, but they got it from the Mesoamerican experimentation in basically domesticating a wild grass and turning it into maize. The ancient Armenians did the same thing with wheat. The origins of wheat are in the Fertile Crescent, particularly in that region, sort of eastern Turkey, from Armenia down to Syria, and all the way to the Persian Gulf is the Fertile Crescent. And their people did a very similar thing. They took a wild grass, saw that it had these little seeds, little tassels on them, and then they bred that, and that's how we got wheat, which is another staple. So ancient people were scientific in their understanding even of the heavens, so that there are very brilliant astronomical observations made by people who never had a telescope. And by that, I mean the Incas and the ancient civilization of the city of Timbuktu in Mali. They had an observatory that even recorded the nearest star to the Earth, which is like amazing. But what they thought was the nearest star, they thought it was Sirius, the dog star, which is very close and it is very bright. It just happens to be a red dwarf that's closer that they wouldn't have been able to see. So we should never see the scientific method as something that is exclusively a European contribution to humanity, because all humans do science, and those scientific discoveries, well, as you'll see in this next video, are really worth noting. This is a good video here that I want to end the class with today. It's now 12:17. I hope it's short enough to the point.
Hey, smart people, Joe here. If your science education was anything like mine, you probably learned about the scientific method. The way that it's taught to us, you make an observation, and you come up with a guess about what's going on, and you test that idea with an experiment to figure out if you're right or wrong. Rinse, repeat, Newton's your uncle, and hopefully you end up with a better picture of reality than you had yesterday. That hasn't always been a thing. Humans invented science. The scientific method, we invented that too. And I want to tell you a story about how that happened. Just follow me in here. Okay, I think I'm too old for this. This is the inside of a bounty castle, and we turned it into a camera obscura. A camera obscura is basically just a dark room with a tiny hole at one end that lets an image of the outside be projected onto this back wall. Now, it takes a lot of light for this to work, but luckily the sun has us covered there. It takes a really sensitive camera to make this shot even possible. But to the naked eye in here, I gotta tell you, this is an incredible experience. It's amazing that this works. What you're seeing happening behind me here is not a trick. Whatever Thomas is doing. This is a direct technological ancestor of the camera that we use today. It's one of the oldest methods of projecting images. And the reason that we're in here is because around 1,000 years ago, a mathematician named Al-Hassan ibn al-Haytham made a promise to the ruler of Egypt that he'd build a dam across the Nile River to stop its catastrophic floods. Problem was, Ibn al-Haytham had never seen the Nile River. And when he got to Egypt, it was way bigger than he expected. And suddenly, it was in a little bit of trouble because the ruler of Egypt was famous for killing or banishing anything he didn't like. Legend has it, he even banished a vegetable. So to cover his mistake, Ibn al-Haytham decided to fake insanity and go into house arrest rather than lose his head. And he's sitting in his dark room. The only thing he had to entertain him was light beaming in through a tiny hole. His room likely acted as a camera obscura, just like this one. In a camera obscura, the image projected from the outside world is flipped upside down, which must have looked pretty strange to somebody 1,000 years ago. In fact, it looks pretty strange today too. But as Ibn al-Haytham studied this light beaming into his little dark chamber, what he found was going to change science forever. Ibn al-Haytham emerged from his imprisonment with all sorts of new ideas about light. He showed how it travels in a straight line, how it bounces off of different surfaces in different ways, how it makes an image in the eye, hundreds of years before thinkers in Europe refigured those things out. Eventually, he wrote a book that laid the whole foundation for what we know about the physics of light today. But all of this wasn't even the biggest impact of Ibn al-Haytham's work. In the process of revolutionizing optics, he pioneered what's perhaps the first version of the scientific method as we know it today. Born in that dark room over 1,000 years ago, today, the backbone of modern science. But what is the scientific method really? Back when he was studying that light hitting the wall of his room, there was no such thing as a scientific method. But there were other ways of making sense of the world. For example, for as long as humans have been humans, they've observed patterns in nature, cycles like seasons and years, what plants made them feel better when they were sick, which seeds would grow into the biggest grains. That let them make calendars, medicines, and invent agriculture. Not bad. What these ancient humans were doing was a key piece of science. They were using observations from the past to make predictions about the future. And ancient people built up tons of knowledge about the natural world this way. But what those ancient people didn't ask is why things are the way they are. Ask an ancient Maya, Babylonian, Egyptian, why the sun comes up or the wind blows. They probably point to a myth or a god, not to astronomy, physics. Then the Greeks showed up. Ancient Greek philosophy dudes were some of the first people that we know of who started looking for natural explanations to things in a really organized way. The Greeks were masters at this thing called reason, basically using logic to explain things. For instance, the Greek philosopher Pythagoras noticed that if you pluck a string, the sound that it makes depends on how long or short it is. And he figured out that the notes in a musical scale aren't random. They're mathematically related to each other. So if scales are defined by math and music is made by scales, he reasoned that math was the basis of all music. These philosophers believed the truth was out there, and reason and logic were the way to uncover it. Those are important ingredients for how science is done today. But there's one key thing those philosophers didn't do very much of: experiments. Eventually, some Greeks began dabbling with experiments. Like one summer day, Eratosthenes observed shadows in different Egyptian cities so that he could calculate the size of the earth. A physician named Galen was setting fire to his own skin so he could test different burn remedies. That's commitment. Experiments let these scholars actually test their ideas about how the world works. Ideas couldn't just stick around because they were good enough anymore. They had to be right. Now, some historians argue that these experiments were actually the seeds of the modern scientific method. But by the 2nd century, the Orthodox Church was getting big in Greece, and the church wasn't that into science. So the experimentation party fizzled out before it really got going. Then, around the 7th century, science was about to have another big moment, this time in the Islamic Empire. It was the largest empire on earth at the time, stretching all the way from Spain to India. Islamic scholars read the works of the Greeks and others and built off of their knowledge, making lots of new discoveries and inventions. Ever heard of algebra? That's theirs. But the scientific method, as we know it, didn't get its start until Ibn al-Haytham got stuck in that dark room.
So remember, one thing he noticed about the camera obscura is that images from out here in the outside world are flipped upside down. So why does that happen?
Ibn al-Haytham reasoned that light had to travel in a straight line from every point on the object outside. So the light rays coming from the top and the bottom cross as they enter the dark room. So that when they hit the wall, they're flipped. But that was just a logical guess, and guessing isn't science. It's what he did next that would end up changing the course of history. He put his guess, his hypothesis, to the test. He placed lanterns in different positions outside the room and looked where the light from each one struck the wall. If you cover one, it disappears over here. Sure enough, the spot on the wall always made a perfectly straight line through the hole to the lamp. So light travels in a straight line. Check. Ibn al-Haytham performed a lot of other experiments in that dark room with a hole in it. The size of the hole, how the moon and solar eclipses looked, how lenses and mirrors bent and bounced light. And he wrote up these ideas about light in what's known as the Book of Optics. He explained all of the experiments that he did in meticulous detail so that others could adopt his method, reproduce his work. He showed that science wasn't just reason or logic, or even observation wasn't enough on its own. It took experiments to find the truth. And after him, there was no going back. Now, Ibn al-Haytham didn't change the way science was done instantaneously. The modern scientific method came together over centuries. And things really got going after a Latin translation of his book began making the rounds in Europe. One of the people to read that was an Englishman named Roger Bacon in the 13th century. Bacon really loved that stuff about optics and light just fine. He really latched onto were Ibn al-Haytham's ideas about how to do science. Bacon helped popularize this idea that science was about experimentation and checking each other's work in order to establish one single scientific truth, which sounds pretty familiar, doesn't it? Plenty of scientists from the time of the scientific revolution have direct or indirect links to Ibn al-Haytham. We know that Kepler and Galileo read his book, and they made a few important discoveries thanks to science. We associate names like Newton and Snell with the origin of the physics of light. But we know Ibn al-Haytham's work was being passed around their circle of friends. So I have to wonder if even the great Newton got some of his ideas from somewhere else. Today, a lot of that old science wouldn't pass peer review, but all of these characters were doing something that at least looks a lot like science as we know it. Each of them uncovered fundamental observations about why the universe works the way that it does. And it's probably no coincidence that many of them had Ibn al-Haytham's book on their shelves. It would be wrong to say that one person invented science because, well, that isn't how science works. But Ibn al-Haytham gave those who came after him a whole new way to explore the world and get closer to truth by making predictions, doing experiments, and most importantly, challenging existing ideas and being willing to replace those ideas with new ones. Today, these are the key parts of what we universally call the scientific method. Although different types of scientists have different ways of uncovering new knowledge, they all trace their roots to this story, this shift in how we seek to explain the world. Science is often looked at and often taught like it's a collection of facts, but that's not really what it is. Science as a practice, as a verb, asks us to be enemies of facts. One thing Ibn al-Haytham seemed to just get was that what we don't know is as important as what we know. Because knowing what we don't know can tell us where we should be looking. I mean, in a way, all scientists are sitting in the dark, looking at the little bit of light let in from the outside world. And Ibn al-Haytham gave us a way to examine that light and get a little bit closer to the truth. Stay curious.
Yes, stay curious. Let me see. Dr. Kanata, stop the share. So it's now it's 2:30. And I'm glad you could hang in there and see everything I wanted to share with you today. So this is our first sort of exposure to the scientific method, but also to a lot of discussion about AI. I'll post the recording of this. I'll stop the recording now. And then when